Hello. Today we're going to use the Helios G4 plasma fib to cut open the apertures on a few local electrodes for our LEAP 5000 local electrode atom probe. So I've got 4 local electrodes in the tool right now. The electrodes are held down to a large, I think it's a 4-inch diameter, maybe 3-inch diameter aluminum stub. And they're held down just with double-sided copper tape on the bottom of each of the electrode pucks. And then I have some single-sided copper tape wrapped around the connection pin of each of the electrodes. If you're ever going to put an electrode into a SEM, it's important to ground that pin somehow to the stage. Otherwise, if you try to image the local electrode, it will charge up very badly, and you will not be able to use the fib on it. You will not be able to cut on it, and you'll have lots of problems. So that's how I do it. So let's go ahead and we'll turn on this tool, and we will see what these electrode apexes look like. Now, I have not looked at any of these yet, so this is sort of a real-time experience of cutting these things open. All right, so let's just start with this one. This is ID MJ. And so let's zoom in here and look at this apex. So if you never have looked at a local electrode, a used local electrode before, this is what the surfaces typically look like. They're usually pretty covered up with all kinds of junk. And all these little protrusions on here are what give you the hot spots when you're running your atom probe experiment. And there's a variety of ways to try to knock these things down and remove them so they don't emit. Now today, I'm not really concerned about knocking down all of these little bumps. I'm going to clean these electrodes a second time once I take them out of the tool, but a lot of these probably are going to get reduced. My main concern is I want to open up these circular apertures to make them more round again, because these little protrusions right here are what block your field of view when you go to do atom probes. So ideally, this is a nice circle. And when they're new, I believe they're usually about 40 microns or so circular diameter. Let's see what this one actually is here. Yeah, somewhere around 40. If you've cut these open with the fib a couple of times, you might start to increase the diameter of that inner circle, and that's not too much of a problem in my experience. If they start to get really big, maybe into like that 50 micron range or bigger, maybe it's time to retire that local electrode. But we just want to get them kind of circular again. So we'll just go through our normal fib setup procedure here. We're going to tilt and find the eccentric height. And then we'll use the plasma fib and the large beam current capability of the plasma fib to open those apertures up again. So let's bring it up to 4 millimeters. And just so we know what we're doing here, we'll take a couple pictures here before we start. I'm going to turn the, let's go to 5 kV. We don't really need any kind of high resolution imaging here. So a little bit more voltage and beam current will make it easier to see what we're doing with the fib cuts. Okay, all right, the detector is on the ice detector for some reason. Okay, so let's just take a nice kind of slow picture here of this edit our image conditions. Let's do 30 microseconds. Apply 3 for this one. And let's just go with a 1000x mag. That's nice. So let's take a picture. So we can go ahead and save this. All right, so let's go ahead and tilt to 52 degrees. Point this thing at the fib. And this local electrode looks like the top maybe got a little smushed. I'm not sure about that. Usually they're not this flat. But we'll see. As far as I know, it still works. So, all right. So we'll go fib. We're just going to cut this at 30 kV. We'll do initial focus with a kind of a small beam current. And then we use the bigger beam currents to really open up the aperture. Fortunately, these you can't really hurt these by fib. They're pretty thick. I think they're a couple hundred microns thick foil, so it takes a lot of abuse to accidentally cut a hole through one of these things. But that being said, we don't want to use the really large beam currents and just sit on them. All right, so that looks pretty good. All right, so let's turn up our beam current. Maybe let's try something like this 0.2 microamps. And these big beam currents are kind of hard to focus, but they should, if your tool's in good alignment, they should be pretty good to start with. But what I'm going to do is I'm going to use a purposely a little bit smaller circle just so I don't want to widen the aperture more than I need to. I just want to get it back around again. So maybe let's try like 35 microns on the outer diameter, and then we'll make the inner diameter pretty small. We'll do like 34. So that way it's just going to cut like a little ring pattern. And let's set this depth to some giant number so this doesn't stop immediately. All right, and let's go ahead and just say that looks pretty good, and we'll hit play. And you can kind of see here in the real-time image where the beam is actually hitting things. So like right here, there's a little bit of a protrusion, I think, or maybe that's a hole. I guess it's hitting all around here. But we'll just let that cut for a little bit, and then we'll take a look and see what the result is. All right, let's stop that. Let's see if we've made this any better. A little bit. There's still not quite where we want it. So let's make this a little wider. Let's take it out to, let's go to 38 microns. Let's see what this looks like. All right, now we're starting to get some cutting here. Sometimes there's debris that gets kind of built up on the inside of the local electrode aperture down in here. This stuff is pretty hard to remove in my experience. You could try to come at it with the fib from like an angle and try to cut that out of there, but I think I'm just going to leave that alone today. Not worry about it too much. Let's see here. We cut a little bit more. And that looks pretty good. So let's stop this and let's tilt this back to 0, and let's see if we've improved the circle a little bit. My guess is that it'll be much more round. Okay. That looks pretty nice to me. So let's go ahead and save that. And if we want to see how big so that's pretty round, and we've only increased the diameter a little bit, about maybe 2 microns from the starting point. Pretty happy with that. All right, so let's move on to the other electrodes. So this next one here is AEK. So let's go over that one. Ooh, this one's pretty ugly looking. So first of all, we'll take our starting picture here. Obviously, a lot of stuff on this one. Let's see, AEK. All right, so this one should be pretty lined up already. Yep, there we go. So we'll just use that same pattern size. We'll just kind of center it as best we can. There we go. And let's hit play. We'll let that cut for a minute. Let's take a look at the SEM snapshot. We'll see how we're doing here. Getting there. that looks, let's stop that. Let's see what it looks like. Always make sure you check it by looking straight down through the aperture. It's really hard to tell looking at it from the side whether you've got it cleaned up or not. So this one, definitely we've got the circle cut out again. It looks like there's some erosion up here in this corner. I'm going to leave that alone because if I cut this thing circular to open up and get all the way up into there, I'm going to increase the diameter of this a lot more than I want to. So let's measure this. How big is it? Yeah, so it's about the same as that last one was after I got done cutting it, about 42 by 42. And again, I'm not going to worry too much about this. Hopefully that doesn't cause any problems with the atom probe experiment. In my experience, it doesn't, but I guess if you wanted a perfectly circular aperture, you could change it. All right, so we'll save that and then put our measurement back on there. I guess I should not have deleted that. Save that with our overlay graphics. Just in case we have to come back here, let's save our position. All right, we'll go on to the next one. So as you can see here, this goes pretty quick with the plasma fib. Just a few minutes for each one. So this one is AYJ. This one's got some nice junk all over it. So once I'm done fib cutting these, I'll take them out. We want to clean the electrodes again to try to minimize any hot spots. So however you're doing that in your lab, you know, whether you're using like the Spark style cleaners, or I like to just use solvent followed by the plasma cleaner to do it. But you know, however you're going to do it, I would do that cleaning operation again after you do the fib cut. So this one looks like it got a little bit bigger. So we might have to increase the diameter. I should have, let me go back and open up that. So this one, yeah, this one's quite a bit bigger aperture. This one's probably one of the 50 micron. So we've got a couple in our lab that are 50, and I think most of them are 40. So this one we're going to have to increase the circle diameter quite a bit. So let's take this one out to 48, and we'll do the inner diameter maybe like 36, 46, something like this. Center that up as best we can. All right. This one's probably going to take a little bit longer because I got to chop through all of this this stuff right here. That's probably going to take another minute or two. But with the big beam currents that you get with the plasma fib, this does not take very long at all to do this cut. Okay, still a little bit of a protrusion there. All right, looks like it's probably cut. Let it run just another couple seconds just to make sure. All right, I think this one's good. Let's go back to 0. We'll check it out. Because this one's so big, I don't know if we want to make this one perfectly circular either. Yeah, I'm going to call this one good enough, just because it's pretty large. About 52 by 52. Okay. Then the last one that I got in here is WK. Go over WK, see what this one looks like. Now this one I've fib cut before. I don't know if you can see the kind of the square marks on here and the damage and things like that. So this is the second time I believe for this one getting fib cut. So you can do this multiple times. And this one looks like it's one of the bigger apertures too. As WK. This one's pretty big. This one's almost 60 microns. So maybe it's time this one gets retired. This one's getting pretty big. But let's go ahead and cut it open anyway, just to do it. So it looks like we got to aim for about a 60 by 60 circle for this one. Might make an interesting research subject. Maybe take a look at what these different aperture sizes do for your experiment. I'm sure Kamika probably knows. Maybe I should ask them. So I've been going about 2 microns undersized, so I'll go 58. Maybe like 55. All right. And you can, we're doing this with the plasma fib, but you can certainly do this on a gallium fib. It's just that it takes a lot longer to do these cuts. The extra beam current that's allowed with this tool really makes this process quick. So because we're using 0.2 microamps, so 200 nanoamps, which is about 4 times the beam current you get on a regular gallium helios, and the resolution of the beam is better, so it cuts faster than a helios at this high current range as well. So with a gallium fib, you'd be looking at more like 5 to 10 minutes probably to cut these circles open instead of just a minute or so. So very doable. Just I like doing it on the plasma fib because it's quick. That's looking pretty good. I think we're probably all set for this one too. So let's go ahead and go back to zero tilt. Check it out. So again, this one's a little bit on the bigger side, but it'll still work for atom probe. You see we've got it, it's pretty circular again, 63 by 63. Just a little bit of an extra bump up here in the corner. Not too bad. Certainly a lot cheaper than sending all 4 of these electrodes back to get refurbished at Kamiko, which that's probably a couple $1,000 versus maybe $100 in fib time to cut them open like this, and then usable again for many more sessions. All right, let's go ahead and vent the chamber, and we'll shut the tool down. Thanks for watching. Hope you give this a try sometime in your own lab, and let me know if you have any questions. You can reach me at the University of Michigan at the Michigan Center for Materials Characterization. Thanks.